publication about wood and engineered wood products and passive house and academia, educating, etc., on how everything works together. So just to get the easy items kind of off the table, why are we building with wood? I mean, there's a bunch of different answers for it, but generally speaking, it's the lowest carbon balance when compared to steel or concrete buildings. And I leave it just simply at that. Passive house, I guess most of you are very much familiar with it. So this is just the lowest energy consumption, and that reduces the environmental impact and the thermal comfort. The one which is much less clear is the prefabrication. So where is that coming from? How does it work, etc.? So, and that's going to be kind of the first half of my time here, focusing on this. But before we start, just a quick introduction about my background. So I came in 2007 to Canada and brought the Austria House way back then with me, which was in 2009 finished and the official first certified passive house in Canada. At the time, it was also the first building which used CLT, DLT, and some other sort of certification. So it has been a first in many different ways. And even though it's a small building, it was a milestone in Canada's construction industry. So prefabrication, stay with me here, just a little bit of journey, so you can close your eyes if you want to. Just imagine you are planning to buy a new car and you go into one of these fancy dealerships and you sit down with a bunch of people, you discuss all the details of your car, the financing, etc. You sign a contract, and then at some point, they will tell you, yeah, it's going to take probably 3 months or so to deliver. So you wait anxiously, you're sitting at home, and at some point, 3 months later, a group of people shows up with several trucks and starts to unload. And so they unload a whole bunch of different parts, you know, the chassis, the body, and tons of different parts. Nothing is really finished. So it rains, it starts to rust, and it gets moldy, everything is wet. So I think I can stop here with my journey. You get it. This is totally ridiculous and not acceptable. So then the logical question is, why would we accept that with our buildings? Why would we accept that kind of approach with something where we spend about 10 times the amount of money on? So if we go back into the construction industry in North America, this is just a picture from about 150 years ago. So this is essentially how we've built 150 years ago. So you have these timber or sticks, more or less, and you just nail them together. And if you compare that to our modern construction industry, well, quite frankly, not much has changed here. Yeah, sure, we have a nailing gun. And yes, the saw is now driven by an electric engine or motor. But otherwise, it's very similar to what we've done 150 years ago. So there wasn't much progress. If you haven't yet, I strongly encourage you to take a look at this report from the World Economic Forum published 6 years ago, which really focuses on the productivity of the construction sector. One of the key findings, and I guess you probably have seen that somewhere else already, if you look at all the different industries out there, exempt is the farming business, because that would be totally off the chart. Over the last 50 years, there was an increase of 150% in terms of productivity. That's massive. At the same time, the construction industry went down by 20%. So obviously the construction industry is currently, at least over the last 50 years, developing in a fundamentally different direction than the rest of all of our industries. Why is that? There's a bunch of different answers. Please read the reports. But one of the keys is that the actual manufacturing process hasn't really changed and is still almost medieval, and not accepts modern technology. So we have to do these kind of things to get back into the green, so to say, and really start to increase the productivity. So when I moved to Canada in 2007, I was just walking through the streets of Vancouver, and I stopped by at various different construction sites and started to realize pretty quickly, they're all built on site. So every wooden building was constructed on site. And that was totally new for me because I did not see that before. So I came to these construction sites and stopped and asked a few people there. So why is it that you do construction on site? Why don't you do prefabrication? And pretty much every time I got the same answer, oh no, that's way too expensive, we can't afford that. Okay. So next time I had a chance to go back to my old colleagues in Central Europe, I essentially asked them the same question. And I asked them, well, why is it that you always do prefabrication? Why don't we do construction on site? And the answer was kind of a surprise to me. Oh no, that's way too expensive, we can't afford that. So it took me a while to really wrap my head around and to figure out, assuming none of the two parties is stupid, so there must be a reason why building on site is more cost efficient in North America and why prefabrication is much more cost efficient in Central Europe. So, and I get to the answer of this relatively quickly here. So, but this is one of the factors which are pushing towards prefabrication. We have several of them. The first one you're very much aware of, I'm sure that's the same across the US as well. We have a problem with labor shortage. So that is really something which is bothering the construction industry. The second one is too high construction costs, and obviously there are many different reasons behind it. All these things are pushing towards prefabrication, but now the new ones, and I think they have the strongest influence of all of them, are code changes. So at least here in British Columbia, we have recent code changes which for the first time force people to actually build something energy efficient. And relatively new, we are also allowed to build tall wood buildings. So these are, at least from my perspective, the two driving factors for a change, which will happen relatively fast. So the first one, in BC, we have this so-called STEP code, the BC Energy STEP Code, which defines energy efficiency targets in 5 different steps, and they are basically distributed over a period of 15 years. We started in 2017, and the highest step should be reached by every municipality by 2032. Step 5 is so-called net zero ready. It's not quite passive house. Passive house would be step 6, but it's already using same or similar matrix to calculate things, etc. So people will be very much used to do these kind of things, at least at 2032, when everyone has to go for something similar. What that means, practically speaking, if we take a look into the history of wood construction, at least over the last, let's say, 50, 70 years, traditional framing, that was a thing of the past, that you got away with a 3.5-inch or 5.5-inch thick wall. In more recent years, at least in BC and some other jurisdiction across Canada, you have to have at least a continuous layer of insulation on the outside, typically just very thin, nothing really major. And it's quite tricky if you do that with EPS and XPS, because now you're running into vapor diffusion issues. But that was kind of the intermediate, a little bit odd step. And now we're really entering into the future that we're building much better performing buildings. If they're truly passive house certified or very close to it, doesn't really matter at this point. So that's basically the future, which started around 2010 with the first passive house in Canada. And since now, I lost overview, we have plenty of it. So, and what it actually means in terms of values, etc., a PhD student of mine did, just on a side, a little study, which was very interesting, looking at the highest energy efficiency step by codes and putting several different buildings into several different climate zones in BC. So we came up with that as a rough rule of thumb, the wall thickness basically doubles, so almost 100% thicker, so 100% more volume, assuming that we still build with the same traditional insulation materials, not with vacuum insulated products. And the other conclusion was that the weight goes up. The third conclusion is that the labor steps go up and the accuracy to achieve the air tightness has to be increased as well. Consequently, it's fair to say without prefabrication, you just don't have cost or a feasibility, financially feasible option to build high energy efficient buildings. So it becomes cheaper to do them prefabricated. And that pressure is on the industry right now. And we can see prefab companies almost popping up like mushrooms across BC. So it's a very interesting and very dynamic development we're sitting in right now. The other thing, as mentioned earlier, is tall wood buildings. We started in the building I'm sitting, that was in 2014, the tallest in North America. Since then, quite a bit has happened. So taller buildings have been built across North America. And it goes without saying, it's very easy to imagine. You cannot, it's not very smart to build scaffoldings that high. So the panels, whatever you do on the outside, has to be finished, pre-finished, so prefabricated. So that's the second driving force here. Without prefabrication, no tall wood buildings. And these two driving factors really define how the next few years will develop in our construction industry. So everything pushes towards prefabrication. And if done right, you have a whole bunch of different advantages coming out of it. A higher accuracy, higher energy efficiency, because you get rid of thermal bridges, etc. You have a higher productivity because you're working in an ergonomically designed environment. Overall, the manufacturing process becomes much more cost efficient. You have a healthy work environment, less sick days, etc. So productivity in general on an annual base goes up. A waste reduction. And then a few more things which are a bit more specific, and we have to be careful what exactly we're looking at. Generally speaking, prefabrication is architecturally very flexible. We can do all kinds of different things. Fair enough. With modular construction, we have a little bit a limitation there, but with panelized, none whatsoever. We can optimize the use of materials. That's a different thing than waste reduction. So now you optimize the actual material put into your construction. And to be frank, even though that might provoke one or two people here, but that is certainly not true for modular construction. Very simple, if you build modules, then typically you build every wall twice or every floor twice. So that's obviously not efficient in terms of material use. And again, and don't get me wrong, I don't want to bash on modular too much here, but with transportation, we have another issue there. I'm shipping a lot of air to the construction site, so panelized has clearly the advantage here too. But all of them have in common that the impact on the building site is much lower. Less dust, less noise, less traffic infringement, you name it. So a whole bunch of advantages for the cities themselves, the inner cities. So already having talked a little bit about panelized and modular construction, I just want to break down a little bit the different types of prefabrication we can use. The first one, the first level, the simplest of all of them is engineered wood products. The second one is prefabricated panels. The third are pods. And the fourth is modular or volumetric construction. So what that means in detail, well, the engineered wood products, they can be either on the light side, so framing packages or trusses you're very familiar with, or they can be on the heavy side, so the mass timber stuff. Careful here, typically in Europe, for example, that's called pre-cut and not necessarily prefab, because you just pre-cut all these different components. Now, when we talk about panels, there is a wide range of, I can close them on one side, I can close them on both sides, I can finish them on one, I can finish them on both, I can add my electrical, my windows, everything in. So the further I push it, obviously, the more advantages I do create. For the pods, we have, generally speaking, bathroom pods or mechanical pods. So these are small, very specialized modules with a very high load of mechanical equipment, hence the bathroom, kitchens, or these kind of things. Quite common, you have a bathroom on one side of the wall and you have the kitchen aisle on the other. So you pre-assemble these things in a controlled environment, and then you lift it on the building site, or you install it into a module in the factory. And last was the volumetric construction. So either manufactured homes, and quite frankly, I think the bad reputation of prefab is a little bit coming, at least in North America, is coming from manufactured homes, because traditionally they were not a superior quality. These are the units which just consist of one box, if you will. As soon as you have two or more, we're talking about modular construction. And now you can obviously put them up. The picture on the right is the building Treat in Bergen in Norway. That was in 2015 when they went up for 15 floors with modular construction. So modular construction is a little bit an issue across North America in terms of how it is done. The usual construction is that you put together your, whatever it is, 2x4s, 2x6, and some plywood or OSB. And as soon as you have a panel, you put them into a three-dimensional structure. And then you continue from there on to add the insulation, the drywall, etc., all these other different things, including the electrical. Well, without wanting to offend anyone here, but with this approach, you're combining the disadvantages of prefab with the disadvantages of site construction. Because the disadvantage of prefab is clearly that you need a large facility that costs money. And the disadvantage of site construction is that the whole process is not ergonomically optimized. Material flow, etc., isn't ideal. Now I combine both of these major disadvantages in one system. That's simply not competitive. So a lot of different options to optimize are just not used. Another thing, and some of you might know what I'm talking about, I found another medieval torture instrument, the ceiling rig. The way it works is you have an elevated table. You should see my cursor, I hope. On top of this table, you build your whatever it is, your panel. And then you have this walkway around here, so the workers can walk around this panel and work somewhat efficiently. Now, the specialty is that this whole thing is elevated, and underneath there's a room where other workers are working. So these are the ones with the back pain. So they are in a certainly much less than ideal situation to work. And so this is something it's widely accepted. You can find in almost every prefab company across North America. At least that's what people are telling me. I visited quite a few, but certainly not all of them. But it seems to be widely accepted in this industry. It's kind of the opposite of productivity here, because the people underneath have a very limited, they're very limited in terms of workflow. Interesting how these things came into place over time. A very different approach would be to finish the panels up to the highest level possible. And then literally at the last second, you're basically putting your panels together into a module, if that then makes sense. So these pictures here are, I visited Boklok. I don't know if you guys are familiar. So Skanska and IKEA teamed up to have a housing unit. So yes, IKEA builds houses, and they also install their kitchens already into the modules. So far, only for Sweden. They do it now since, I think, 10, 12 years. I have no doubt that they're aiming for world supremacy, but so far it's only Sweden. Highly efficient production line, so everything is quite optimized. You will always find potential somewhere, but they are already pretty far. So just for the first portion of my presentation here, when we talked about prefabrication, 3 important things I want you to remember. The first one, prefabrication is not the continuation of the same construction process in a manufacturing shop or in an enclosed environment. That is not prefabrication. Prefabrication is much more. Prefabrication is the change of the entire process that starts with the design and goes through the engineering and every other steps in between and includes the manufacturing. The manufacturing is clearly done differently than if you would build anything on site. So you try to optimize the entire process all the way through. And ideally you achieve something what I would refer to as mass customization. Each and every building can be still very individual and different, but the system, the hidden system behind it, what nobody sees when you have the finished building, that is optimized and much more efficient. The second one, to utilize the full potential of prefabrication, panels or modules have to be delivered to the building site as complete as possible. You want to have as much included as possible. Because if you're working on large tables, it's just much quicker to install the window or whatever it is. So you want to go as far as you can whatever the industry currently allows, or for that matter, what the code allows, but take it as far as you can to get as much of the productivity advantages out of your prefab plant. And last but not least, prefabrication can offer any architectural style, because I know that architects, I mean, that's my own experience. So any architectural style is possible. I would even go as far to say that prefabrication offers new architectural styles and stuff we haven't dreamt of in the past. Just this one, for example, is not a rendering, it's an actual building. Without prefabrication, you can obviously not build any kind of parametric design in a cost-efficient way. So now we're switching over to the mass timber component and the educational component. As mentioned earlier, so I am located at the University of Northern British Columbia, and I am located right now, I'm sitting in the Wood Innovation Design Center. This is this building. Some of you might have seen it before. It was built in 2014, and back then it was the tallest wood building of modern times. Because I figured in downtown Vancouver, for example, was a wood building from 1906, which was actually the same height. And I'm sure you will find old buildings across New York or Portland or wherever you are, somewhere in the Harbor District as warehouses. There are probably old buildings left which have a similar height of somewhere around 30 meters or 100 feet or something like this. So we are located, and this is just a map, you can see where, Seattle, Vancouver, Edmonton. Right here is a huge fiber basket. So this is basically all forest. And so in the center of this forest area is Prince George. And Prince George is where the campus of University of Northern British Columbia is. Looking at it on a map, it's actually pretty much in the center of BC, so it's not even in the north. But anyhow, the reason is we're in the center of the largest fiber basket, Canada's largest fiber basket. And so we created here in 2014, I started this work to build a new master degree. So it's a Master of Engineering, course-based, quite fast-paced. It's an integrated wood design. So what we've done is basically putting a little bit of wood science and material science into the degree. But then the largest column is the structural engineering. So the connections, the seismic design, engineered wood products, and mass timber. We are not touching stick frame. So we're not talking anything about light construction. We are just focusing on engineered wood products or mass timber. The second largest column, if you will, is the building science aspect of building physics. So fire, acoustics, vibration, which are all quite crucial in wood construction. And then everything which is related to energy efficiency and passive house, the air tightness, the vapor diffusion, the thermal performance, the thermal bridging, all these kind of things. And we call it integrated because we're bringing two very different disciplines together. So the structural engineers and the building science or building physics experts. And my rationale for this was pretty straightforward. The structural engineer who hasn't understood what a thermal bridge is in our day and age useless. So we have to have structural engineers who really fully understand how important thermal bridges are, because they're most of the time responsible for them. And then we top it off with a little bit sustainable design, life cycle assessment, these kind of things, and processing and prefabrication. So that degree, the first intake we had in January 2016, we started. And since then, so we went through several cohorts and generations of students from, I lost overview, I think 20 different countries or something like this by now. So starting this program, I started to realize, and the program is located in this Wood Innovation Design Center. I figured out relatively quickly that the lab we have in this building, which is here at the base of the building, is way too small. I don't know exactly what they were thinking with the design, but for construction-related research, the lab was way too small. And then we also had an election in 2015. Ours went a little bit smoother than yours. Anyhow, so we got a new government, and one of the first things the government did was starting an infrastructure funding for institutions of higher education. And I thought, this is our chance. So I went to the facility management team of the university, and together we applied for funding to get a new laboratory building, so the Woods Innovation Research Lab. So we wanted to build this in passive house quality. I think I don't have to go through what passive house quality is, so all the different thresholds you have to pass. Just something amusing, I can't really withstand the urge for my American friends. So the 10 watt per square meter equals 3.171 British thermal units per hour square foot. I'm not sure if you're all aware of it or what consequences that has in your daily life, but ASHRAE 90.1 defines a semi-heated space for more energy consumption. So according to ASHRAE 90.1, a passive house is an unheated building because you consume less energy than a semi-heated building. Not sure what kind of code implications that has in your daily life. At the same time, a passive house fulfills the ASHRAE comfort criteria A. So we get the highest thermal comfort in a building which is, according to ASHRAE, not heated. I mean, that there is a vast conflict of interest if the American Society of Heating and Refrigeration, air conditioning, is responsible for energy efficiency targets, so basically make themselves obsolete. That goes without saying, but I'm sure you have enough discussion about this in the US. So we had the honor to basically be in a position to have the first indicative design. I'm not talking about the architectural design, the facade, but essentially what the functions of the buildings are, how big it can be or should be. And that was actually the first cohort of our students was part of it. So with them, we developed together the idea to build this lab. And we also said, well, if we build something up here, we have to do it in passive house standards. So passive house keys with compactness, etc., you're all familiar with. But the specialty for us was now the red basically symbolizes the entire envelope. So you have, so to say, a cube with 6 sides. And you have a large envelope, but at the same time, the yellow is just the treated floor area, and the treated floor area is pretty small because the building, so we have 1 mezzanine, a small portion of it. Theoretically, the volume of the building would have been good for the green portion too. So in other words, we had to be 3 times more efficient than a usual passive house because we only have 1/3 of the floor space a typical building would have had with, you know, it's 10 meter tall. So we have 3.3 meter per floor height, so to say. So 1,000 square meter floor space and 10,000 cubic meter of volume, basically, was for the building. So that's fairly large. And so we had to find a solution how to deal with this not so ideal ratio of envelope area to treated floor space. So the specific challenges we were dealing with was to prefabricate this passive house was the very small treated floor area in comparison. The second one, and that was rather unique, the consortium of companies, architect, engineer, etc., and contractor who won the bid on this project, well, for them, they were inexperienced. They've never done a passive house before. They've never done any kind of prefabrication before, and they've never done any kind of airtight envelope before. So it was one of these odd times that the clients actually knew much more about construction and of this kind of stuff than the professionals who got the contract to do it. But it worked out very well because they were all eager to learn about this stuff. The second set of challenges was rather technical stuff. So thermal bridges, etc., that's pretty straightforward. But we had some unique challenges. We needed a large bay door for trucks, for semi-trucks to get in and out. And we needed a large dust extraction system to get rid of sawdust. So those things were quite specific challenges. Plus the climate. In the winter, it's going to be cold here. So let's say adhesive and other things don't work in the winter. So you are limited in terms of your time frame when you can do what specific types of work. So this is the location where we started. It was a parking lot before, so they had to clean it out. Then we laid down the insulation, so that's 25 centimeter of EPS, 10 inch underneath, and skirt around this of 25 centimeters, so fairly well treated thermal bridges to the ground. Another cohort of students was now involved in equipment or equipping the building with sensors, thermal sensors, humidity sensors in various different positions. So that was a nice research project, and we published several papers since then. So in various layers, sensors were pre-installed. Then the rebar on top, the light or lighter color in the middle is flow heating, so a meandering system of floor heating. That was the easiest way to get this little tiny portion of energy into the building. In the background, you see literally tons of rebar. This is for the strong floor and the strong wall. And so this is when they were pouring the concrete of a 1 meter thick concrete wall with literally tons of rebar in it. And that was about a time when, well, that was after your election. So the running joke in the city was, if the lovely southern neighbor really goes nuts, hide on the other side. So it's a very stable concrete wall, which will withstand all kinds of different things. Prefabrication, so the beam or post and beam system was all prefabricated, including the connectors. And then that was put together relatively quickly. Again, another set of students. Here, the lady with a red helmet, she was responsible for an LCA, so life cycle analysis, and really looking into trying to always be before and not running behind, but being before the design team and influencing the design. And in several different ways, we were successful. So we were changing types of materials, etc., to less environmentally harmful stuff. Obviously, it would have been much better if this would be integrated directly into the design phase, but still, even that student had quite a bit of an impact on the building. One of the bigger challenges was the insulation. So we needed 50 centimeter of insulation, that is around 20 inch. Initially, we wanted to have I-joists. They were coming from the US, but delivery time was way too long, costs were way too high. So we settled for something what the people in the north do really well. We built trusses. So now the wall system is basically built with trusses. Another group of students now installed a bunch of sensors into these walls in 3 different locations in the depth to get a nice picture throughout the wall depth. We did this numerous times in various heights of the wall and in the south and north facing walls. Those sensors, the vast majority is still working. And again, we published a few papers about the performance of the building. So those sensors were good to, on the one hand side, to also track the thermal performance, but then also the humidity inside these wall cavities of a type of structure which hasn't been built before. So prefabrication, as I mentioned, there was not much no experience with prefab in the region. So the contractor did find a team which was at least capable of putting together these wall panels, the trusses plus a OSB layer on the inside and a membrane. But that was it in terms of how far we could take it. So insulation wasn't in, windows were not in, electrical, etc. was just not installed yet. One of the key challenges with passive house is the air tightness. So wherever those panels were attached to each other, when we look from the outside, so we have the trusses and then the membrane underneath, and where the transition of the panels was, this had to be taped, and then you achieved a very airtight envelope. All other kind of penetrations were treated equally. And then all the things which are not included in that prefab package had to be done on site. So that means, for example, the insulation on top of the roof, which is between 50 and 70 centimeter thick, EPS mainly. And the wall cavities were filled with blown-in insulation. At the lower portion of the picture, you see this one guy blowing in mineral fiber. Mineral fiber because it allowed us to slip into a different kind of fire hazard category for the insurance. So initially we wanted to do cellulose fiber, but then settled for mineral fiber. And as you can imagine, I mean, all these steps have to be done on site in a not so favorable climate. So it was very cold. And in fact, it was that cold. So pretty brutal for the people to work there. The bay door worked out very well. There's not much choice. And to the best of my knowledge, there's still only one company who offers you a decent air tightness. Not perfect, but good. So the left picture shows a little bit the system, how you can, it's a bit crude, but you can still adjust the pressure of your door into the seals. So that is a good feature. But still, I mean, you can see here, for example, there's some light shining through. So the door is not airtight, but it's the best you can find. And then you have here the white stuff is the ultra high molecular weight to reduce the friction on the rubber seals. And overall, it worked really well, the system. So we achieved a decent air tightness for the door. Another big one was the dust extraction system. So if you just blow out the air, obviously you would have to have a massive makeup unit and no way that you could ever achieve any of the passive house goals. So we had to go for a recirculation system, but to make that legal, we had to have really high performance cyclone filter on the outside, plus then very fine filters on the inside. So the large box you see there, that's the filter box. It has to be maintained, but it works really well. So we measured quite a few times now the dust content inside the air, and typically it's lower than on the outside of the building. So very good air quality. The air tightness, the achievement, that's probably the one where you've heard about the building before, if you did. So at 50 Pascal, we achieved 0.07 air changes per hour. And to the best of my knowledge, it's still the North American record holder. I have not heard about any other buildings in North America achieving a lower air tightness of 0.07 for both the pressurization and depressurization. So following the international protocol for passive house. Yeah, it's a bit dry to say the result is pass. I thought I would prefer if they would have said sensational. But yeah, so we passed this with a 0.07. Just to give you an idea, I'm holding up there a sheet of paper. It's a letter size sheet of paper folded in half. And that's almost exactly the equivalent leakage area of the entire building. So that is fairly good for this size of building. The official certification, so we achieved the heating demand of 12 and the heating load of 10. Since then, we are measuring and monitoring the buildings. So to be frank, our heating demand is slightly higher. It's hovering somewhere between 16 and 18, depending on the climate and the winter. We still have some research projects to try to figure out what exactly the reasons are. We found a few different ones. Typically, they're related to the controlling of the mechanical system. For example, in the first winter, we figured out that the cooling system kept on running, and this was only became obvious after the cooling system completely freezed at minus 30 degrees. So little hiccups here and there with the controlling system of the mechanical part, but overall good success, and the heating costs are equivalent to a code-conforming single-family home. To put that in context, these are all the buildings except one, which were built on our campus. And the little one down here, that's the Wood Innovation Research Lab. Putting it into perspective that the room is 10 meters tall, and we have a real challenge with treated floor area versus volume, and the dust extraction system and the bay door for semi-trucks, it's quite impressive to see them in comparison to other buildings. In the meantime, the facility management building of the campus is also now a certified passive house. So that's the second on campus. And from here on, I'm very certain every new building is going to be a certified passive house. and utilizing mass timber. So the facility management office building used CLT. That was the building, our lab building, shortly after we moved in. And just before this talk here this morning, I went over and took another picture. This is it now. So now you can see it hustling and bustling. So there's a lot of stuff going on. We do a lot of testing for mass timber projects across North America. For several projects in Toronto and other areas, we did testing in our facility. It is the largest structural testing facility in Western Canada. And the nice thing for me personally was that the small lab in our office building is now a building science lab. So that's where we do acoustics, vibrations, thermal performance, thermal bridging, those kind of testings. So without much further ado, that was it. This is the building as it looks basically today. And thank you so much for your attention. Are we doing Q&A now or later? Ken, what are you saying? Or Mike?
I'm not sure what Mike has planned here. Let me see if he can.
Sorry, I was muted. I was trying to get. So we don't have any questions that have come through, Guido. I have I think one or two quick ones if you don't mind.
Sure, shoot.
So the building science integration is really fascinating to me. Having worked in both the US and in Germany, I would say there's not a strong component on building science, especially oriented around passive house buildings as there is in Europe. Can you speak a little bit more to the adoption of that? Is UNBC the only program in Canada working on this? Are you in discussions with other programs to kind of broaden those offerings in other places?
You're certainly right. Building science is underrated across North America, and it's also underrated across Canada. We're not the only one. We're the only one who combines wood construction, passive house, and building science all into one program. But we're certainly not the only one who is working on building science. So other universities have small units typically focused on building science as well. I think the only thing which is really special about us is the combination to not just having passive house in there, but also having the collaboration with wood construction and mass timber.
No, that's great. I would say the other thing that I'm really fascinated by, and you mentioned code changes. Again, looking to my time in Europe, it felt like not every village maybe, but every district had the capability. There was a firm that could do prefabrication of buildings, similar to this, or multifamily housing, basically across the board. We definitely haven't seen that uptake in the US, although that's starting to change. But British Columbia has really been a leader, I think, on the prefabrication front. And do you think that in the US, our building codes vary even next to adjacent jurisdictions, right? Whereas in the EU, there's kind of more conformity with the European codes. Do you think that that plays a role in kind of the adoption, or are there other factors?
Well, so the other, well, no, I think absolutely. I mean, typically how it works in Canada is Vancouver as a city, it's a chartered city, they have their own building code, they always push first. They have a fairly, for lack of a better word, call it green or sustainable mindset. The BC code is typically following right thereafter, depends on the court cycle, it might be 2-3 years or so that they adapt very similar goals of Vancouver. And then typically it takes another 2-3 years that Ontario follows. And well, if Ontario follows, half of Canada has basically followed. And then eventually it comes into the National Building Code. So we can see how things are progressing through the industry. I'm also in the BC Step Code Committee. And the idea of having the step code, the 5 different steps, was basically copied from the European Building Directive, where we had something similar. And for the longest time, I kind of had the feeling that by basically defining new energy efficiency targets, that on the political side, it was maybe not fully understood that this means a radical shift in how we build. Sure, theoretically, you can build a passive house on site, and many people have done that already. But to do it cost efficiently, prefabrication is clearly the way to go. And you mentioned Germany or other Central European countries. I grew up with, professionally speaking, with prefab, right? So I've never seen people building on site because the energy efficiency codes in these areas were already stringent in the 80s or 90s, as we are now starting to develop in BC. So there was just this time lag, but essentially that makes it easy for us to predict what's going on here. So just because of economic, because of an economic push, we will go towards prefabrication because building on site thicker envelopes and more airtight envelopes is just not really cost efficient. So it will change the industry. We've seen over the last 2-3 years that really prefab companies are popping up like mushrooms. We will see how many will survive. But it allows, one of the really positive things is, I guess, it allows the rural areas or outside of these big centers, it allows those companies to participate in the boom of big centers. I dare to say that we won't see, if any, but not much, prefab companies based in Vancouver, for example, because real estate is too expensive to have a large facility for production. Salaries, etc., cost of living is so much more expensive. So you will run your prefab plant outside of the major centers. That decreases the costs, but at the same time, there's a social aspect because it allows other areas to participate in the boom of large centers.
Okay, and I think we've hit our time. There are a couple of other questions. We'll try to fit them into the Q&A afterwards. Thank you, Guido.